Greetings, everybody. Um, on the Georgia View page, I've posted two practice exams for Exam 2. And notice this is Exam 2, Practice Exam 1. And in this video, I'm going to go over the solutions to problems 1, problem 1, 3, and problem 5, because those problems are not UCM problems. I'll do the UCM problems in the second video. So I'm going to go over the answers to problems 1, 3, and 5. And I may break this video up into two videos, but I'm going to do the UCM problems, and they're going to be in separate videos. Okay, so let's look at problem 1. It's a penguin sliding at a constant velocity. You know, we don't really care about the numbers, what they are, but because you plug them in at the end. But he's sliding down an icy incline with a constant velocity of the 1.45 meters per second. The angle of the incline is 9.75 degrees. Then when the penguin gets to the bottom of the incline, it then slides onto a horizontal patch of ice. Then you're given that the coefficient of kinetic friction, mu k, is the same for both the horizontal patch and the incline. And I'm asking for two things. Part A, I want to know how long does the penguin slide on the horizontal patch before stopping, meaning his V final is going to be 0. So I want to know how much time does he spend on the horizontal, how long. And I want to know how far does he travel, what is the distance x along the horizontal patch. So I want to know again, I want to know t for the horizontal patch, how long in seconds does it take for the penguin to stop. And then I want to know what is x on the horizontal patch. How far does he travel along the horizontal patch before he stops? All right, well, so this is a case where you combine Newton's second law. You have to apply Newton's second law to both the incline and also when the penguin is on the horizontal. So you have to apply Newton's second law to the penguin when the penguin's on the incline and when the penguin is on the horizontal. So you're applying Newton's second law to incline and horizontal. Then, because once he gets to the horizontal, the penguin eventually comes to a stop. So on the horizontal, they have some V initial, which is non-zero. We know V final is 0 because the penguin stops. So we have VI, VF, we have a distance x, and we're going to have an acceleration a. So we're also going to have to apply one or more of the 1D kinematic equations. It's a very, very standard problem. Let's go ahead and let's set up the solution. Well, again, we're going to do you treat the incline and the horizontal separately. So let me go ahead and start with the incline. And here's the penguin on the incline. Okay, theta is the angle of the incline. Remember, we're doing incline first, then horizontal. So let's not worry about the horizontal right now. Well, remember, the penguin is sliding down the incline at a constant velocity, a constant speed. That's what I indicate right here, telling you, hey, the penguin is sliding down the incline and the speed is constant. Well, let me draw all the forces acting on the penguin. There's mg, again pointing in the original negative y. There's mg. There's Fni, meaning that's the normal force of the incline on the penguin. Now remember, the penguin is sliding down the incline, and you're told that there's friction. So if he's sliding down the incline, Fki, meaning kinetic friction force on the incline. Fki is directed up the incline. Now again, by now this should mean second nature. Mg into its components. The x component is mg sine theta. The y component is mg cosine theta. Because the penguin is sliding down the incline, that represents the positive x direction. So mg sine theta is positive, Fki is negative. Well, let me first, now our approach is, we know that mu k is the same for both horizontal and incline. Well, let me apply Newton's second law to the penguin, and maybe that can get me mu k somehow. Well, again, remember now, the speed is constant, meaning a is 0, meaning the positive x must equal the negative x, and the positive y must equal the negative y, because they have to add in their respective directions. All the x forces have to add to 0, and all the y forces have to add to 0. Well, it's very simple. There's only two forces in the x direction. One's positive, one's negative. They better equal each other. There's only two forces in the y direction. One positive, one negative. They better equal each other. So in the x direction, we get Fk. Oh, let me pause this for a second. Okay, so we're just dealing with the incline. I've got all the forces on the penguin. I've resolved mg into its components. Clearly, Fki must equal mg sine theta. And Fni must equal mg cosine theta. Because again, what does the constant speed mean? A is 0. Meaning, in the x direction, the forces have to add to 0, and in the y direction, the forces have to add to 0. Well, very simple. Okay, so we have that. Now remember, in general, well, we know that Fki is mu k Fni, or again, coefficient is friction force divided by normal force. So the coefficient mu k is Fki divided by Fni. Well, so I'm taking equation 1 and dividing it by equation 2. So on the left-hand side, I have Fki divided by Fni. That's my mu k, but I'm just dividing equation 1 by equation 2. So on the left-hand side, I get Fki divided by Fni. Well, I know that's my coefficient. I know that's mu k. Well, on the right-hand side, I have mg sine theta divided by mg cosine theta. Well, the mg's cancel. I just have mg sine theta divided by mg cosine theta. That's a very common technique. That's why I wrote them in this order. So I'm just taking equation 1 and dividing it by, I'm just taking equation 1 and dividing it by equation 2. And that gives me mu k, which is Fki divided by Fni, is equal to tan theta. Well, I know theta was given. Theta was the 9.75 degrees. So I get mu k is the tan of 9.75 degrees. Make sure you're in degrees mode. And you get 0.172. Now we're done with the incline. We don't have to worry about it again. So we got mu k. Why is that good? Because we know mu k is the same on the horizontal. So we're done with the incline. Now let's look at the horizontal. Let's apply Newton's second law to the penguin while it's sliding along the horizontal. Well, remember, its speed along the incline is constant. So when it gets to the bottom of the incline, it's when it first touches the horizontal, it has some initial speed vi. Well, that vi is going to be v. Because the speed doesn't change until the penguin gets to the horizontal. Then, as it slides along the horizontal, which this initial speed vi equal to v. Because remember, right when it hits the bottom of the incline, the speed is constant, so that speed is v. But that's the initial speed for the horizontal. So the constant speed along the incline becomes the initial speed along the horizontal. Then he travels some distance x in a time t and comes to a stop. This is before stopping. So Vf is 0. Well, let's just look at while the penguin is sliding along the incline right here in between initial and final. Well, the forces acting on the penguin are the weight mg, the normal force of the horizontal pushing on the penguin, I'll call it Fn. It's not the same as Fni, but it doesn't matter, it's Fn. And remember, if the penguin is sliding along the horizontal in the positive x, Fk has to be in the negative x. So those are the three forces acting on the penguin. Well, I know right away that on the horizontal, Fn has to equal mg, because those are the only two forces acting on the penguin in the y direction. the penguin is not accelerating in the y direction. So Fn has to equal, so in the y direction, that's what I mean when I write y with a colon. I'm just saying that's Newton's second law in the y direction. Right away, Fn equals mg. Well, what about Newton's second law in the x direction? Well, there's only one force acting in the x direction. It's Fk. And it's negative. So Newton's second law in the x direction is minus Fk, well, again, equals ma. Sum of the forces, they can be positive or negative, sum of the forces equals mass times acceleration. So in the x direction, I have minus Fk equals ma. Now again, Fk is always equal to mu kFn. So I've taken the x equation and I've replaced Fk with mu kFn. That's what I've done from this step to this one. I've just replaced Fk with mu kFn. The minus sign is still there. Well, now what the y equation tells me, well, what is Fn? Well, Fn is simply mg. Okay? So I now have equation 3. Minus mu k mg equals ma. Now, why did I do that? Well, I want to solve for a, because remember, the penguin is accelerating on the horizontal because the speed is changing. He's going from some v initial, some non-zero v initial, to a v final of 0. So we know the acceleration is going to be negative, and so he has this constant negative acceleration. So I'm going to solve equation 3 for a. Well, nothing complicated. A is simply minus mu k times g. What is mu k? I got that in part A. So I'm good. I know what A is. Okay, so now let's look at what I'm asked to solve for. Again, now we're on the horizontal. Remember, we're done with the incline. I want to know how long the penguin slides on the horizontal before stopping. I want t, and I want to know how far. So I want x and t for the penguin on the horizontal. Well, let's use 1D kinematic equation 2 to get t. Because equation 2 states Vf equals Vi plus At. I know Vi and I know Vf. I know A from when I solved equation 3, so I know A. The only unknown in this equation is t. So, basic algebra, Vf equals Vi plus At. Vf is 0, so I get 0 equals Vi plus At. Solve for t, you get minus Vi over A. So minus Vi over A. Well, remember, what is A? A is minus mu kg. So that's where that comes from. In the denominator, what is A? It's minus mu kg. So the minus cancels, and plug in your numbers. And remember, the initial speed on the horizontal is the constant speed along the incline, because his speed doesn't change until he gets to the bottom of the incline. So that initial speed with which the penguin begins to slide in the horizontal, that's just the constant speed of the 1.45 meters per second down the incline. Okay, so you get t is minus Vi over A. What is A? Minus mu kg. The negatives cancel. Plug in the numbers. You get 0.860 seconds. Now I know t. Now I need x. Well, I'm not going to use equation 2 again, but I could use equations 1, 3, or 4. I'll use equation 3. Remember, it says that's the general equation. Vf squared equals Vi squared plus 2ax. Well, I know Vf is 0, so 0 equals Vi squared plus 2ax. Solve for x. You get algebraically, you get x is minus. Notice in the parentheses, the Vi squared is in the parentheses. It's not minus Vi squared. It's the negative of Vi squared over 2a. Well, again, what is A? Look in the denominator. What is A? A is minus mu kg. So you get minus vi squared over minus 2 mu kg. Because what is A? A is mu kg. Minus signs cancel, plug in the numbers, and you get 0.624 meters. Now, you'll get the same value. It'd be worth it to try use equation 1 or 4. And I guarantee 100% you're going to get the same answer. Alrighty, so let me go ahead and save this video. Let me pause it for a second. Yeah, I just changed the acceleration. I put it in green. So every time you see an A, you'll see it's in the green, and A is minus mu kg. That's all I did. So let me go ahead and save this video.